Hi, I'm Sunil, CEO and founder of Nanoprecise. Two most important metrics for any predictive maintenance solution are false positives and false negatives. Without having a true information about these two metrics, a predictive maintenance solution or a predictive analytics solution is nothing more than an astrology tool or a fortune teller tool. In this video, we will explain how Nanoprecise is dealing with false negatives and false positives, and what is the strategy to keep these numbers low. We will be covering a basic intro about the industrial machinery system, followed by which we will look for analogies between the predictive maintenance approach, followed by a doctor for a human patient and for an industrial machine. We will then define and understand what is an anomaly and a fault and different fault types existing in the industry. Then we will delve deeper into the false positives and false negatives. And finally, we will understand what really is customer requirement with respect to false positive and false negatives, and how to define an effective strategy for reducing these two. The whole point of sharing this video is to share the knowledge that we at Nanoprecise gain so that we can collectively improve and enhance the predictive maintenance industry and win customer trust, no matter whoever is the vendor. Let's think about what are all the parameters that can be monitored in the system. All those parameters can be classified into two categories: process parameters and system response parameters. The process parameters are things like flow, temperature, flow rate, current, speed, etc. While the system response parameters are things like vibration, acoustics, magnetic, flux, surface temperature, speed. And these are basically the system's responses to the changes in the process parameters. What is the most complex machine in the world? Certainly a human body. And there are a lot of similarities between predictive maintenance approach for a human body and industrial machinery. So how does the whole process of predictive maintenance work for a human body? A human body has 5 senses: smell, see, hear, touch, and feel. So when we feel something wrong or we detect something anomalous with our body, we go to the doctor. So this first phase is done by our body, and it's called anomaly detection. And once we go to the doctor, he or she recommends a lot of tests, and using the results of those tests, diagnoses the issue. This second stage is called fault diagnosis. And finally, once the patient is notified of a disease type, such as cancer, his first question is, how much life do I have? The doctor, using his or her years of experience, dealing with multiple patients for a specific type of disease, which can be called as an AI, even though it is a natural intelligence, but the principles that the doctor is using in his brain on the data he gathered over the years are applicable to AI that is used in even corporate world, right? So using this analysis data he has developed in his mind over years, he will tell the patient what is the remaining time he has till the cancer inhibits the normal function of the body entirely. And this final step is called remaining time to failure prediction. Now, for the pump and motor assembly, all these 3 stages and objectives that are applied for predictive maintenance of a human body can be exactly applied to an industrial machinery, with an added stage called root cause analysis, which is not the main focus of this particular presentation. So let's now understand what is an anomaly. As per Oxford Dictionary, something that deviates from what is standard, normal, or expected is called anomaly. Anomaly detection will tell what's abnormal, but there's a crucial difference between abnormal and bad, because not all abnormalities are bad. Anomaly can be either good or bad. It is just a deviation from the normal. Anomaly detection will miss most true, false, and alarm on things that are just normal abnormality. To give you a simple real-life example of anomaly with the human body is, let's say you have a smartwatch, and if I, as a doctor, have recommended you to tie that to your arm all the time, and if the oxygen reading hits high, I will immediately send you help from the hospital. Just imagine You were jogging on a late evening and oxygen levels hit high. Is this a problem? Maybe, but definitely not worth sending an ambulance and the whole medical team. And this is an example of an anomaly. And this is why, a reason why anomaly can be just a normal abnormality. It does not necessarily have to be a fault. And that's why we detect anomalies based on some outlier values or some abnormal trends, but we don't classify them as something faulty with a specific component in the machine yet. Anomaly detection is mostly based on point data, not on the spectrum data. So based on the point data, we can simply only tell if something is abnormal or not. We cannot tell what exactly is causing this anomalous or abnormal behavior. Now, some real life machinery examples of anomalies in an industrial machinery, such as pump and motor system, when they have a cavitation or an air entrainment or air recirculation. Other than this, there may be other type of anomalies, such as a sudden change in raw material or input material type at a particular time, which may not occur again, or anomaly due to sudden sensor non-performance, but that does not show again. All of these are process-related phenomena, which will not cause immediate damage. They can cause damage in the medium to long term, but they themselves are not faults. Now let's understand what is a fault and how is it different from an anomaly. A fault is an issue with an individual component or multiple components within a machine, which can both degrade the normal performance of an individual component of a machine or can ultimately lead to machine failure. And this can happen with a specific component inside the machine in a specific failure mode. Fault detection can tell what's bad and not just what's unusual. And once the fault is present within any component in a machine, it cannot be rectified unless the condition of the machine has been altered in some physical way. What this means is that, for example, if you have a bearing problem, the bearing problem will not just go away. Unlike an anomaly, when suddenly one will notice a high vibration, but that will just subside. While in case of identified fault mode, such as a bearing fault, even though the vibration may or may not subside, its overall level will be increased from before, and very soon it will start increasing again unless there is some action taken to fix the bearing issue. And gradually, the vibration or temperature or acoustic values can creep up to the catastrophic value. So what this means is that fault is something that is a long term and will not subside unless some action is taken. Fault will always be preceded by an anomaly of some sort, but fault itself will never precede an anomaly. An anomaly does not necessarily mean a fault, but having a fault means there was some anomalous behavior sometime in the past. We can detect faults based on spectrum data because spectrum data can give us the same kind of accuracy as a fingerprint matching technology, fingerprint matching, using a biometric technology. So what are the different types of faults? There are mechanical faults like bearing, gear or shaft issue, electrical faults like stator, rotor winding, and structural, and there are some kinds of faults like instrumentation, like the fault in the machine control panel. Out of these three, at least at Nanoprecise, we focus on the top three, which are detectable using the 6-in-1 sensor and the AI algorithms that we are bringing. So what are false negatives? Basically, a test result or a software inside that indicates that a machine does not have a specific faulty component, when in fact the machine actually does have the faulty component, and the same fault mode leads the machine to a failure and leads to downtime, is called a false negative. Three conditions are very necessary for incipient fault condition to be called a false negative. The fault mode which ultimately led to the failure, and the machine must be detected, or the fault mode which ultimately led to the failure of the machine, and it should be detectable by the PDM solution. There should be variation in vibrational, acoustic, or thermal energy due to this fault mode that should be evident by the sensor data. It should actually lead to a downtime, to a failure or an equipment failure. And these three conditions are very important to really say that there was a false negative. So just because an equipment failed where the sensors are installed, it cannot be called as a false negative. For it to be a false negative, the equipment should fail due to the malfunctioning of any of the component, any of those fault modes which I talked about, mechanical, electrical, or structural, or malfunctioning of any of the components such as shaft, gear, bearing, impeller, winding, rotor, resistor, etc. And the fault mode in these should be detectable by the PDM solution. And there should be some variation in the data of at least one of these fault types, or at least any variation in the metrics from vibration, temperature, magnetic flux, or acoustic data leading up to the failure. Some people may argue that the sensor might give a wrong data or may not be collecting the data at a sufficient frequency. Well, it can be easily figured out through various ways if the sensor data quality is good enough and whether leading up to the failure, the sensor data quality has gone bad or not. Through various handheld analyzers and also through statistical techniques, the above scenarios can be nullified or be proven true. Regarding the frequency of the data, if the equipment has failed within just few seconds or few minutes, such that none of the sensor data reflects any variation and frequency of the sensor data collection is higher than the time taken between fault origination to fault actually happened, if that's the case, even that cannot be called as false negative, because such rapid faults that can happen due to any number of reasons, such as operator error, an accident, even sensor will have its own limitation. Every sensor will have, and at what frequency it can collect the data. And once the technology has been selected and its minimum possible frequency has been approved, any failure on equipment that is caused due to a fault that progress much faster than that minimum possible frequency possible by a system cannot be called as a false negative. It has to be at least detectable by the sensor, because if the data does not show any variation at all, software is just analyzing the data that it gets. If there is a specific kind of fault that the solution is supposed to detect and the solution did not identify the fault, and if that leads to catastrophic failure, that's a false negative. Having false negatives can be very dangerous for the reasons that it can completely cause mistrust and can cause massive monetary loss for the customer in terms of lost production or reputational loss by jeopardizing the safety of the personnel. And due to the above reasons, the industry has very low tolerance, almost 0 to 5% for the false negatives, especially if the equipment is semi-critical. It is almost zero. For example, Boeing for 747 Max, everybody knows how much damage it cost in terms of valuation loss for the Boeing, and also the reputational loss, and so many lives lost because of those issues that Boeing 747 had, which can be called as false negatives. Now, what are false positives? If a PDM solution generates an insight that there is a fault, but actually there is no fault, that's called a false positive. And having false positives can be somewhat dangerous too, because they influence human behavior. Just like false negatives, false positives builds up mistrust in the solution. And after 9 false positives, believe me, the 10th one, even if correctly diagnosed by the solution, can be easily missed because the user is just fed up of the false positives enough that it has influenced his or her behavior. Apart from this, false positives can also cause unnecessary extra work for the customer, costing more in resources and time. A good example of false positives, ultimately leading to the demise of a company itself, was Theranos, as we all know. A lot of their blood samples showed very high value of LDLs and HDLs or triglycerides, leading to totally inaccurate diagnosis. And when the same samples were checked with other FDA-approved labs, the results were starkly different and not as scary for the patients. And certain patients who saw the Theranos results actually went into depression, which when checked with other labs were not at all true. And that's what is the impact of a false positive. It influences human behavior in either taking a completely wrong step or just not trust the data anymore. But what is not a false positive? An anomaly cannot be called as a false positive. If a certain fault is diagnosed in a machine, but if that solution is not meant for detecting those faults, in that case, it cannot be said that the PDM solution gave a false positive. Also, if the fault is diagnosed by the solution, but its intensity is somewhat debatable between what the solution highlights and what is the situation actually at the site, This also does not mean false positive, of course. As long as the solution shows the intensity of the fault to be same or somewhat higher, not too higher, of course, than what is found on the site upon visual inspection, it should be okay, because ultimately the aim is to avoid unplanned downtime. So what is an ideal customer requirement? It's very simple. A customer wants both false negative and false positive should be lowest, basically zero. The customers we have seen that are adopting predictive maintenance, either in oil and gas, mining, steel, pharmaceutical, HVAC, usually don't focus so much on the false negative, because by default, the end user assumes that the system will at least be able to avoid or notify in advance all false negatives without any issues whatsoever. But when in fact, this should be of much higher significance to the industry. It's really the false positives which customers think that the PDM solution may not be able to filter properly, which may lead to extra work and change in human behavior. Because it leads to extra work in the near term, and that's what they're worried about. More than 90% of the notifications that is generated through PDM solutions these days are purely anomaly related, which has nothing to do with false positive. But unfortunately, some users misconstrue an anomaly as a false positive and make a perception that the PDM solution is sending way too many alerts. Yes, anomaly notifications can and should be reduced over time, but it is important to identify even an anomaly and report it to the customer, because it's not necessary that only a certain type of fault mode that is detectable by the PDM solution will lead to catastrophic failure, or a failure can happen due to any kind of reason that are not attributable to electrical, mechanical, or structural faults. And thus, this kind of anomaly notification at least will cover those undiagnosable faults and ultimately helps in the larger cause of avoiding unplanned downtime. A thing to realize is that false negative and false positive are both completely contrasting in nature. That means a strategy to achieve a low false negative rate can lead to somewhat false positives, and a strategy to achieve zero false positive rate can lead to few false negatives. So how should an end user decide their strategy? According to us, false negative should be given the utmost importance, and right next to it should be the false negative. Because even if there are some false positives sent, it may somewhat increase the human effort in the near term, yes, but all that effort is paid off or compensated by avoiding one big catastrophic failure, which can cause a big unplanned downtime and cause millions of dollars of production loss. This is why we at Nanoprecise promise less than 1% false negatives and less than 5% false positive, even though our aim is to achieve 0% of both. So how does Nanoprecise reduce false positive? So as we talked about the 3 steps: anomaly detection, fault characterization, and the remaining time to failure prediction. So we do comprehensive work at the first step itself, which is anomaly detection. You can see that 90% of our notifications or more are purely related to anomaly detections. And with a clear and honest philosophy, we differentiate anomalies from the fault. So as you can see, we have rated our notifications in multiple severity level, level 1, level 2, level 3, 4, and 5. And up to level 3, we don't even notify it as a fault. However, we do notify any anomalies right from the start, but don't call it as a fault yet, as we are not exactly sure it is a fault or not. We just call it as an anomaly because till that time, we're not sure exactly what is the issue. In this way, we are not just able to reduce the number of false positives and false negatives, but are also able to balance off the 2 contrasting objectives of ensuring 0 false negatives and low false positives by holding off the fault alerts till it reaches a certain advanced stage. For equipment, fault mode diagnosis is one thing, and reporting it is another thing. A plant technician who mounts anti-friction bearings on a shaft can tell you that 30% of a bearing life is reduced at the installation stage itself. Does that mean we start showing fault alerts from the day 1? No. Thus, it is important to just notify the fault just at the right time. Not too early, not too late. And a lot of science and maths goes into determining what is an apt time to notify the customer. We promise our customers with more than 95% confidence on false positive. How are we able to ensure such high confidence? As I told before, that we apply the same philosophy or concept for machine fault detection that is applied in fingerprint matching through biometric technology. Let us take a typical vibration spectrum. I'm just taking vibration data as an example, but the principle holds true for any kind of data such as acoustical data or magnetic flux spectrum data. Of course, not all types of faults can be detected with one technology. For example, vibration and acoustic data is good for detecting mechanical faults, while magnetic flux data is good for detecting electrical faults. Let's assume on a typical frequency spectrum captured by Nanoprecise machine doctor sensor. Usually, we will have 8,000 lines of resolution. In this picture, you will only see 100. It's just a zoomed one, but usually you will see 8,000 lines of resolution coming from a Nanoprecise machine doctor sensor because the data is taken at 16 kilohertz sampling rate. So half of that is the number of lines of resolution, maximum number of lines of resolution, which is 8,000. So we need to identify what is the probability that a spectrum taken at a time t contains a fault. For this, we need to first understand what exactly means, what exactly is meant by a fault on a spectrum. In the world of vibration analysis or condition monitoring or signal processing, a fault is said to have occurred when the two peaks are exactly coinciding with the harmonics of the fault mode. For example, if you see this particular peak and this particular peak, for example, if this was 20 hertz, for example, and this was 40 hertz, this will be a harmonic of each other. The other harmonic will be at 60 hertz, other will be at 80 hertz, likewise. And if this is related to bearing outer race failure fault, that will be called its fault frequency, and these four are its fault harmonics. So if the spectrum shows two highest peaks exactly at these two fault frequencies, we can say that it reflects a fault. So we need to determine if at random we take a spectrum, what's the probability that it consists of a fault? So the number of ways in which the first peak can occur, is 8,000, because you can select, out of 8,000 lines of resolution, you can select a peak. A peak can exist in any line of any of those lines of resolution. So the number of ways in which the first peak can occur is 8,000, and the number of ways in which the second peak can occur is 7,999, because except this at this frequency, you can choose the second peak at any of the other frequencies. So the total number of ways one can select two random peaks on any spectrum is 6.4 into 10 to the power 7, as shown here. Usually for any fault mode that can be detected with spectrum data, the first two peaks are of primary concern, even though one can extend it to multiple harmonics, such as gear faults, which exhibit early stage failure at even 20th harmonic or even 40th harmonic of gear mesh frequency. For simplicity's sake, we will consider a fault frequency of 20 hertz and its first two harmonics at 40 hertz and 60 hertz, as I mentioned before. In an ideal world, let's assume that every frequency on a frequency spectrum relates to some fault. So the number of ways we can select the first harmonic of the fault is 4,000 ways, because really, if let's say you have to detect every possible fault, we can detect 4,000 possible kinds of faults from this spectrum, because there are 8,000 lines of resolution, and the second harmonic of each of these faults in the first 4,000 lines will exist in the between 4,001 to 8,000. So that's the total number of ways one can select a spectrum such that it for sure reflects a fault is 4,000, because the second harmonic you can't just select. It has to be dependent on it is just a multiple of the first one. So the number of ways is 4,000. So now if we calculate the probability that if a spectrum is chosen at random, what is the probability that it consists of a fault? It's simply 4,000 divided by 6.4 into 10 to the power 7, which is 0.0000625, which is pretty low. Now, if the technology is even able to identify peaks with more than 95% accuracy, its accuracy will be 0.95 multiplied by 1 minus 0.0000625, which is close to 94.99%. That is if the technology is able to identify the peak with more than 95% accuracy. But the reality is that as long as the frequency resolution has been properly maintained, it's very easy to achieve more than 99% accuracy. So in that case, one will see almost 99.99375% accuracy of this technology and detecting the fault accurately. So in summary, a typical strategy to reduce false positives and false negatives should start with a solid anomaly detection. But ample care should be taken in training and notifying the customer that anomaly notification don't need to be taken with the same level of seriousness as a fault notification, while at the same time to not completely ignore them, as there can always be faults that are not detected by the PDM technology that the customer is using, but those undiagnosable or undetectable faults can actually cause to failure or a downtime. Apart from this, every fault should be notified at an appropriate time, not too early, not too late. And this judgment of appropriate timing comes with sophisticated and proprietary algorithms coupled with domain knowledge. With the above, one can always understand what is false positive or a false negative and what is not, and how to interpret various types of notifications and ultimately keep the false positives and false negatives low while ensuring zero unplanned downtime. Thank you.